Moving on in our study of logarithms, we want to now talk about the rule of sames, or the base rule of sames, the bros rule as I like to call it. I guess a lot of people don't call it that, but I like to give it little mnemonics like that to help me remember some of these rules. And the rule of sames says this, that if we have the same base of log on both sides of our equal sign, then the values of those logs, as in x and z in our case, they're the same. And the same goes for exponents, that if we have the same base of exponent on both sides of our equal sign, then those exponents themselves are equal. And so these things help us solve problems when it comes to this. So we're going to look at example 3 now on page 329, and we're going to use the base rule of sames, or the bros rule, to help us solve for this. In part A, we have y equals log base 2 of x, and it says to write that in exponential form, and so that's the first thing we'll take care of. So our base is 2, our y is y, and our x is x. So 2 to the y equals x. Okay, part B says, well, hey, use this form here and find y when x equals 8. All right, so we're finding y, as in 2 to the y we don't know, equals 8. All right, so this is a great time to take advantage of the bros rule here, especially for exponents. So what we want to try to do is, can we think of a way to turn 8 into a power of 2? And what I can think of is that 2 to the third power is the same as 8. And so what I'm going to do is I'm going to rewrite 8 instead of as 8, but as 2 to the third power. And what this does now is it gives us the same base on both sides of this equal sign. And the bros rule says that if the base is the same, then the exponents are equal. In our case, that means that y equals 3. So we just found y by using that rule. In other words, y equals log base 2 of 8 means that y equals 3. And that's really what part C is about. So we're going to skip over part C because essentially we just did part C. But let's look at part D, because we're going to use the same rules that we just did for B and A, really, to get to our D. And in D it says evaluate log base 4 of 16. Now what I like to do is I like to put that y value in there. Even if the book doesn't put it in there, I like to have it because now it meets our definition that we see up in the corner here, right? When we talked about in the last example that y equals log base b of x, that we can solve this. So what this is saying is 4 to the power of y equals 16. And once again, we say, hey, can 16 be broken down into some power of 4? Well, sure, because we know that 16 is nothing more than 4 squared. And again, once we have the same base on both sides, it's fairly obvious what the y value is going to be. Y equals 2 in this case. So evaluating log base 4 of 16, even though they didn't put y in and we did, really we could say is the answer is 2. That's another way to say that one. And then they do have a part E here. And part E says, what is log base 10 of 0.001? And again, I'm going to stick our y value in here so that we have it. Let's move over to the left so we have some space to do this one. And what this is saying again is 10 to the power of y equals 0.001. So if there was a way to write 0.001 as a slightly different way, I think we could see this happening. Well, there is. If you remember that 0.1 is the same as 0.10, that's the same as 1/10. So 0.001 actually could be rewritten as 1 over 10 to the third power. Kind of interesting thing there. And then 10 to the third power, right, as in 1 over 10 to the third power, we rewritten again, right, because we don't necessarily like to see a fractional value there. But what we can do is we can say, hey, we can take advantage of the fact that this is going to be 10, and because it's in the denominator, another way to write this would be 10 to the minus third. And with that, now our bases are the same, and so now we get to say that y equals -3. And so we make that look good by rewriting it a little bit. The other way to think of it too is how many decimal points would it take, or how many decimal point moves would it take to get this decimal point so that this wasn't a decimal answer? And that would be 1, 2, 3, because that would make 1. And what is our answer? It's 3. It's negative 3, meaning that we move this decimal point 3 spaces to turn it into a non-decimal number. And we moved it from a decimal to a non-decimal, which is where that negative comes from. So that's another way to think of this as well to get the answer. But the bros is the way that we want to do this, right? We want to say, let's get the same base on both sides so that our exponents can be equal, and then we can solve for it.